give few lectures on particle physics. And in fact, this topic was divided in two parts. One is introduction, and more specifically or essentially, this is experimental and phenomenological derivation of the standard model. And we will discuss how the standard model, its structure emerges from experimental data. The second part is standard model itself with its gauge structure, with spontaneous breaking of the symmetry. And this part will also contain physical consequences or genetic consequences. Tell me, do you see well the blackboard?
Yes, it's okay.
Okay. So what is the standard model? Standard model is the Lagrangian of a certain type. Written in terms of the fields of quarks, leptons, gauge bosons, and Higgs boson. Once you know this Lagrangian, using the rules of quantum field theory, you can compute all observables. So that the present of our course, actually, I will give the first part, introduction to particle physics, and the second one will be given by Goran Simjanovic next semester. So we have experimental data. Observations. We use some principles. You know better I start to write it in different places. So let me see. Yeah. So let me write it in this way. Here. So experimental data. And we use certain principles to describe this data. And from the experimental data, I will show you how the structure of the standard model appears. Well, essentially, we can derive from experimental data, from observations, the structure of the standard model. And so once we define the standard model, formulate it, we can make computations of observables or make predictions. So constructing the standard model, one of the important principles is analogy. And first of all, analogy with quantum electrodynamics. And you will have this course in parallel. So, construction of the standard model heavily based on analogy with quantum electrodynamics, although there are some qualitative differences also. Let me say that every good model of theory should give some predictions and go beyond the experimental data it is based on. So you use some data, construct the structure of theory, and then the theory should give you predictions of some new phenomena so that you will be able to test the model and be sure that you are on the right track. The goal of my course, one of the goals, is to explain how do we get information on particles. So objects which we cannot see by usual eye, and we need to arrange our observations in such a way to get this information. Now, what is the meaning of the information about particles? And then, as I said, I will show you how the standard model structure emerges from observations. So to say, I will give you phenomenological derivation of the standard model. Questions? Okay. So my course will have 3 parts. The first one is lepton and hadrons. And I will describe how the particles are detected. I will discuss main discoveries as well as notions and conceptions. And concepts. So this is the first part. The second part is quarks and leptons. So in this part, we will go from hadron level to quark level. And also I will discuss quark-lepton symmetry. The third part will be devoted to symmetries in particle physics. So I will discuss again experimental and phenomenological motivation to introduce symmetries, some motivations. And I will discuss consequences of different symmetries. Questions? So before I will move further, I want still to ask you the following question, everybody. So how many of you had the courses on nuclear physics?
I had.
One?
Me too, Professor.
Yeah?
Me too.
Me too.
Yeah, me too.
I also had.
Now
I also had.
Now the courses in particle physics, how many of you had particle physics courses? I'm asking this because I will adjust the course according to the audience. So that's important.
I don't have particle physics course.
I had an introductory course on particle physics.
Yes, I also had an introductory course on particle physics.
Yeah, I also have an introduction in the same.
Okay, so I hope at least you will be able to meet in person, not just in a group, but I'm usually inviting students to meet and ask in details about the level of the courses they had in the universities, if they had some thesis, and so if they need some help, etc. But this will be in individual way. So let us start the course. And the first question is, what is a really elementary particle? Because what we will talk about mostly about elementary particles. So the question is, what is an elementary particle? So actually now, when we are talking about elementary particle, we mean quark or lepton or W and Z or Higgs boson. So first of all, use that another one. Okay? So this is quantum object. Although in some aspects, these particles behave as a classical object, but really correct description is given by relativistic quantum mechanics and quantum field theory. Second,
Excuse me, Professor.
yeah.
The last couple of seconds, the video freezes, so none of us was able to see the part from quantum objects. The video just freezes, so we missed this part. Could you please repeat it?
So do you see this?
Yes, we see the blackboard clearly. The video like pauses for a minute, so we couldn't like follow you up.
Oh, okay, so what does it mean that this is quantum object? This means that production of particle propagation and interactions with other objects are described by relativistic quantum mechanics or deeper quantum field theory. Okay?
Okay, thank you, Professor.
Now, the second is that usually we refer to elementary particle as structureless object. So it looks like a point-like. It has no structure. It has no substructure. So we think that all these objects are almost like a point-like, so they're point-like objects. They have no structure, at least for time being. And we know that in history of physics, this concept changes. So people saw that atoms are the most elementary particle. Then it was realized that they have nuclei and electrons. Then nucleons, it was supposed, are elementary particles. But then it was realized that they have quark structure. So the story may still repeat, but for time being, it looks like these particles are structureless. Now the question is, how do we know, how we establish that particle is structureless, is point-like? Tell me. So how we test that some object is structureless, at least at some certain level? If someone has an idea?
We can try to break it down into smaller objects. If it didn't happen, then for now it is elementary. If it did happen, so it's not.
So you are saying we can try to split it and to see if there are some components will appear, right?
Yes, exactly.
Okay. Now, what else can be done?
We can,
How
we can try to observe its interactions with other particles whose structure we are actually aware about to notice how they interact and maybe infer on its structure.
True. What is the most sensitive way to check the structure, the size of the object? I'm sitting because microphone unfortunately only here in the computer, so I need to sit down to listen to hear you. Yeah.
Scattering experiment.
Right. So this is what I want to discuss. The most sensitive way to test the structure or existence of structure is to perform scattering at very high energies, as high as possible. Now let me spend some time because this is a conceptually important question which will actually appear in various other places of my course. So I will start from essentially classical situation, a classical setup, which actually was used essentially by Rutherford to discover nuclei. So let us consider some object with electric charge Q. which is distributed somehow in the volume or sphere, better to say, for simplicity, of the radius RB. Suppose we have probe particle which scatters on this object. The particle has momentum P, and particle scatters with impact parameter, which is the distance between trajectory of the particle at large distances from the object to the axis. So this is impact parameter, RH. Okay. So for definiteness, we can consider the force, which is given by Q, proportional to Q over the radius square, like electromagnetic force, but everything can be generalized to other forces too. So the particle moves, it scatters, interacts with our charge and scatters. So let us consider first the case when impact parameter is bigger than the radius of this sphere. So this is RB. And the question is, what is the angle of scattering? So we can say that here is initial momentum, and then after scattering, it has P prime momentum. And we are wondering, we are talking about the angle between initial and final momentum. So that's the angle theta. Clearly, the smaller the impact parameter, the stronger is scattering, and theta is somehow inversely proportional to impact parameter. And this is because the closer particle moves to this body, the stronger force it will suffer, and therefore it will have bigger scattering angle. So the picture is that we have initial momentum, final momentum of probe particle, and this is angle theta. We can introduce delta P, which is the change of the momentum. And this delta P equals P multiplied by sine theta. So delta P essentially is given by this vector, right? The difference. And that's given by the momentum multiplied by sine angle. So I assume here that collision is elastic so that the total momentum doesn't change. So moduli of momentum doesn't change. Okay. Now, considering this scattering, one can find that delta P is given by Q over RH, where is this impact parameter. So one needs to make just integration along the trajectory, knowing what is the force to solve the equation, and you will get eventually this expression. In fact, this expression can be obtained just on dimensional ground, because the distances, and I will discuss this in more details in the second part of the lecture, has inverse dimension from momentum. And therefore, the only quantities we are dealing here are this RH, and therefore delta P should be somehow inversely proportional to the impact parameter. So what is important that when impact parameter is bigger or much bigger than the size of the object, then effect of the scattering doesn't depend how the charge is distributed here in this sphere. Things change when we consider small impact parameter, when RH is smaller than RB. So I don't see. Do you see this part? Because we have microphone here. So now we have the situation when the radius of our scatter is bigger than the impact parameter. So, and in this case, what happens that our probe particle spent part of the time inside the sphere. So this is again H, this is RP. When particles spend time inside the sphere, so let's take, for instance, this point, in this point, you probably know this trick that actually what affects, or the force which acts on this particle, is given by the charge within the sphere, which is smaller than whole the sphere. If you have spherically symmetric distribution, of course. Do you know this situation? So, which means that outer part, so this and this do not contribute, or the forces which are created to charges distributed here and here, they cancel each other. And therefore, the only what affects the motion of our probe particle is the charge which is inside this sphere, which is smaller than the total radius. And this, of course, happens when impact parameter is smaller than the radius of our scatter. Questions? It's clear? So what is this charge which is inside this smaller sphere? Roughly, it can be estimated like QH is total charge, and here RH over RB cube. So here I assume the distribution is uniform for simplicity, just to illustrate the concept. So what happens when the impact parameter becomes smaller than the radius of scatter? Then the effective charge, which affects motion of our probe particle, becomes smaller than total charge. And therefore, the force and the scattering will be weaker. Well, if the particle moves exactly in the center along this axis, it will not even scatter at all, right? So which means that here we have kind of suppression of the scattering once impact parameter becomes smaller. Now we can write that delta P momentum change is given by QH over the radius H, and inserting the expression for QH, I will get Q RH square over RB cube. Okay? So now let me plot this dependence of delta P, which is the change of the momentum, as function of impact parameter, RH. At large impact parameters, we have this 1 over RH dependence. And below we have this R square, so it will be like this. And here is some transition region. And this point is precisely RB. At impact parameter equals to RH, RB, so we have maximal value. This is delta P maximal, which is achieved when we have impact parameter equals RB, which means that particle moves exactly in this way. So its impact parameter equals to RB. So here is 1 over RH, and here is RH squared. So this is dependence. And delta P maximal equals Q over RB. We can invert this expression and write that RB equals Q over delta P maximal. Or we can write this as Q over P theta maximal. Sine theta, I have even, if the angle is small, then it will be just theta maximal. This means that measuring maximal delta P or maximal angle of scattering, we can find what is RB if it is not known in advance. This is precisely what Rutherford faced with when he discovered the nuclei in atoms. So what was the experiment? I will probably say this later a little bit. So Rutherford has studied scattering of alpha particles on nuclei. And he observed the angle of scattering. He has some screen sensitive and just observe how the particle, alpha particle, scatters. What is the angle of scattering? What was amazing observation? The observation was that the angle of scattering was an average of the order of 1 radian. So the key observation of Rutherford was that the scattering angle is big. Now, if you have the sphere, as it was supposed before, which is filled by, say, positive charge, and this sphere is of the radius of atom, and it was known what is the size of the atoms already at that time, then you would expect very small angles. Just using this relation, so that theta is Q over P and RB. This is Q, right? So from this relation. So he knew what is the momentum of alpha particle. And if you use here, say, radius of atom, then you would get that the angle is something like 10 to the minus 6, which means that all the particles, all alpha particles, are expected to move along the original direction. But what he has observed that actually θ is of the order of 1, which means that the size of the region in which nuclei is sitting is much, much smaller, 5 orders of magnitude roughly, smaller than the size of the atom. So actually then the structure was like this. This is what he has arrived. That this charge, which is in nuclei, should be actually concentrated in much smaller volume than the atom itself. Okay? Actually, we will see that similar picture will repeat when people established that proton and neutron are also not a kind of elementary objects, but they have substructure. Again, studying scattering of proparticles on protons and neutrons, it was established that it looks like the charges are not uniformly distributed inside the proton and neutron, but are focused on very small objects inside the proton and neutron. Now, there is another interpretation of what we just discussed. Let me write again this dependence, delta P, and it was something like this. And suppose we consider scattering of accelerated particles on some object. Delta P is smaller or equal of initial momentum of the particle, right? And if we have particles accelerated till certain energy or certain momentum, then we know what is the maximum delta P. And suppose this delta P is such that we are somewhere here. So we are not reaching this maximum. This means that we can probe with this particle the structures which are here and bigger. And we are not even reaching this RB. And in this case, for this scattering, particle will look for us as a point-like particle. Now, you see here we deal with impact parameter, which is here in this region, which is much bigger than RB. So, and in this case, we also have momentum, or in which actually gives us the de Broglie wave. So lambda is 2 pi over P. And in this situation, the Broglie wave is much bigger than the size of the object. Well, actually, if we change the radius RB, then you would have the pictures like this, or like that, or like this. And for all these radiuses, here we have the same dependence. So in this case, we are not sensitive to the size of the object. So if P is small, lambda, the Broglie wave, is big, then the situation like this. Now I'm jumping onto a wave picture. So we have particle of small size, and then the Broglie wave is much bigger than the size of the scatterer. And this situation, we are not sensitive to structure of this object. To be sensitive to the structure of this object, we need to have small, or very small de Broglie waves, so that we need to have big momentum. We need to have the situation when the object is like this, and the de Broglie wave is smaller than the size of the object. In this case, we can probe the structure. This is similar to microscope. To see small structures of the object we are exploring, you need to have microscope with a very small wavelengths. In such a situation, you are not sensitive to the structure, and the scattering effect will be very small. So you need to have the de Broglie wave, which is smaller, much smaller than the object itself, and then you can see what is the structure. So bottom line, to see smaller and smaller structures, you need to have small de Broglie wave, and therefore bigger and bigger momenta of scattering particle or probe particle. Questions? No questions? So let me come back to our original question about the structure of quarks and leptons. So we need to have scattering with momenta as big as possible. And the biggest momenta are achieved by LHC, which are in, say, several TeV region, 6.5 TeV for time being. And what we need to do is to see the scattering and how it is affected at this high PT, or high momentum. So the setup is the following. At LHC, we have scattering of protons onto protons. And what happens is that then when these protons collide, they produce many secondary particles. And there are events when you have these secondary particles which are within so-called jets. They are not uniformly distributed, but they kind of focused in certain streams. Now, what you can do, you can measure so-called transverse momentum. T, which is this one, which actually resembles to what we have discussed, just the scattering and change of the momentum. So this is PT, and it is given by approximately the energy of jet and the angle. What you can explore and find number of events with a given PT. Of course, LHC observes many, many events, thousands, millions of events. And then they have different events have different PT, transverse momentum. And you can construct distribution. And it looks like this. It also resembles what we have discussed before. So this is what is predicted if you assume that the quarks are point-like particles. So this scattering at LHC, and we will discuss this in details later, can be considered as scattering of quarks within this proton and this proton. So you have essentially beams of quarks at LHC. And therefore, final results here is the results of scattering of quarks on quarks. So here quarks probe particle and also scatter simultaneously. But anyway, you can compute what is expected PT. And you can measure this, and so experimentalists measure this dependence, which is nicely in agreement with what you expect if quarks are point-like particles. If quarks would have some substructure, then you would expect some deviation from this picture, this dependence. So this is number of events and this is number of PT. And I put this kind of histogram because what experimentalists are doing, so they use some small intervals and then count the number of events in these small intervals. If quark would have some substructure, then one could observe, for instance, something like this. Some cutoff, for instance. Well, it depends on the real model of the structure of the quark. But for time being, no deviation from this point-like scatters picture has been observed. And therefore, it allows to put the bound on the radius of quark, which is, again, you can come back to our example as like 1 over P maximal T. And so the radius should be smaller than the maximal transverse momentum. Then we do not see any deviation from the point-like structure. And since P maximal is around 60 EVs, using this relation, you will get that the radius of quark should be smaller than 10 to the minus 18 centimeters. Let me remind you that the radius of proton is 10 to the minus, or maybe, so some of you know this, the radius of proton is 10 to the minus 13 centimeters. And so here we deal with distances which are 5 orders of magnitude smaller. So the radius or substructure of quark, if it exists, should be smaller than 10 to the minus 18 centimeters. Now, another important scale is so-called radius of weak interactions, which we will discuss. And just to say this in advance, that the radius of weak interactions, the most short range interactions, is 10 to the minus 16 centimeters. So this is the best bound on so-called compositeness, if you want, that if quarks are composite objects, that the sizes of this object should be smaller than 10 to the minus 18 centimeters. Questions? Okay. So this is kind of introductory lecture, and we will discuss various things in more details later. And of course, you can ask more questions. You can ask it now, or you can we can kind of arrange meeting in the office or in terrace here. So let us continue with definition of elementary particles. And we said already that this is quantum object which has no structure. Now, next in definition is that this object, elementary particle, is described by set of characteristics. Parameters and quantum numbers. There are two types of these characteristics. One are so-called external characteristics. And that includes mass, which is invariant of Lorentz invariant, which is E squared minus P squared, by spin, so this is angular rotation freedom, degree of freedom, and parity. Who knows what is the parity? If somebody knows what parity is,
Yes.
okay, tell.
So if we change x coordinate to -x and y to -y and z to -z, if the value of the field changes its sign, it's negative parity. Its parity is -1. If it doesn't, it's +1.
Yes, yeah. Okay, so this is the property of the wave functions of quantum objects with respect to reflection of coordinates. X, go to -x. It looks like not very important on the first side, but we will discuss, this is a very crucial characteristic of the particle. So it's a property of particle with respect to this reflection of the coordinates. So let me write this property of wave function with respect to this reflection. So the wave function can change the sign or may not change the sign. So it looks like some kind of symmetry, right, of your object. These characteristics are characteristics of propagation. Of particle. So these are kind of features of the external space, right? The properties of particles with respect to propagation in external space. Another set of parameters is so-called internal characteristics. That includes electric charge, spin, color. I will explain this later. What is this? Now, Vk is a spin. hypercharge baryon number lepton number let me write it here. So lepton number and these characteristics are characteristics of interaction. Remember, the first set was characteristics of propagation in the external space, and these are characteristics of interaction. These characteristics give us classification of particles. It provides with selection rules. Which means it tells us if some processes can occur or some not. And in fact, most of them actually turn out to be coupling constants. Just look at the electric charge story, and this is quite similar objects. So, which means that particle is this object, structureless, which is characterized by all these physical quantities, spin, Q, I3, weak, hypercharge, baryon number, lepton number. Very important thing, I put here parity also, right? So parity. Very important thing that these characteristics are characteristics related to symmetry of space-time. These are so-called internal characteristics, and they're related to so-called internal symmetries. Which are realized in internal space, in contrast to external space, use of coordinates. So these symmetries, which are behind these quantum numbers, are related to transformations in this internal space. Whereas these, mass, spin, and parity, are related to transformation in external, our configuration space. You see that actually behind all these numbers are some symmetries or symmetry features. And this is why symmetry is very crucial for all particle physics. In fact, this is universal language of particle physics. And many things are just can be expressed in terms of symmetries. And this is what we will discuss in details in the second part of the course. So let me just say that leptons are particles, and these are charged leptons and neutrinos, and they have lepton number 1, -1, and baryon number 0. In contrast, quarks, like U quark, D quark, so they have baryon number 1/3 or -1/3 for antiparticle, and they have lepton number 0. So of course we will discuss this in great details during the course. So now very important conceptual thing. What we think that if you tell me that I have object with certain values of these parameters, I know this object. I know how this object will propagate and interact. So this is what actually contains information of a given particle. If I know this, I know about the particle. I know how it will be produced, how it will propagate, and how it will decay or interact with other particles. Okay? So again, elementary particle is structureless object which is characterized by these physical quantities. Questions? Don't hesitate to ask questions. Now let me say one important thing. All these quantities, all what I was saying is our model of elementary particle. So you should not confuse two things. Something which is in reality and all these characteristics. So if you have electron, it's not something which is some body which is written that electric charge is 1, right? It is something, right? And we describe this using these parameters, using quantum field theory, quantum mechanics. And all this is not reality, but this is our description of reality. This is a model of reality. So creating the theory, we are doing mapping of something which is moving in reality or exists onto our mathematical formalism. Or we are kind of creating mathematical formalism which reflects as much as possible features or properties of real world. In this connection, there are two important questions. One is this description complete or not? Maybe we are missing still something. Maybe still there are some other characteristic, crucial characteristic, which we have not yet introduced, but which exist. So for time being, it seems that this provides correct description of what we observed so far. Although, for instance, we probably still missing so-called flavor physics, which I will discuss later. Maybe there are some other quantum numbers which are kind of responsible for flavor physics, I will discuss later. So the one who knows this, some physics which actually distinguishes, say, electron from muon or tau lepton. We don't know what is really difference deep apart from mass. And maybe we need to add something more, some more quantum numbers here to describe this flavor physics. So this is the first question. Second question is, how precise is the picture which you have created? So how exact? Theory. So all these characteristics are embedded into the standard model. And this question can be formulated in different way. Is the standard model is finite theory of elementary particles, or you need to extend it, or maybe something else, some bigger structure exists in each standard model is embedded. So I will come to these questions many times during the course, but just remember, so we have our formalism, which is our image of the real world. And of course, one needs to keep in mind always that it may be not complete and it may be not precise. And this is why we are doing some precision tests for the theory. Okay. Questions? So if someone may maybe just ask something, because I'm not sure, so there's a silence from your screen, and I'm not sure that you are following or not.
Yes, Professor, we are following, and I have a question.
Yeah.
In the parity part, when you say that the wave function coordinates will transform to the minus coordinates, the spatial part, the wave function should satisfy Schrödinger equation or Dirac equation? I just wanted to make sure.
Well, it doesn't matter because these are linear equations, right? And if you just look at these equations, right, because you have wave functions everywhere, so that doesn't change. Dirac equation is also conserving parity. But what is less trivial is when you introduce interactions. The interactions may not be so trivial. And then in interactions, you really will see the difference when you have one parity or another one. Okay? So if you have Dirac equation, right? It's linear with respect to wave function.
Yes.
You have derivative and you have master. And therefore, if you change the sign of the wave function, you will have the same equation.
Yes.
Okay.
I was just wanted to make sure that at this point we are considering the Schrödinger equation for the particle, or?
Well, I'm not considering any equation for time being.
Okay.
Right? So I'm not discussing, and we will discuss parity to a large extent later. Okay. And where this change of the sign of the wave function plays crucial role. So what we will see later, of course, it's just free equation of propagation. It doesn't play any role, so this parity, you can make this transformation. However, when you introduce interactions, then it becomes important. For instance, weak interactions do not conserve parity. And therefore, that has important physical manifestations. But just propagation, it doesn't matter. Okay?
Okay, thank you, Professor.
So let me, I have still, I think, 15 minutes or so to discuss units and scales in particle physics. Which is another very important issue, and many developments and many important problems are actually connected to existence of different scales in particle physics. So in the course, we will use our standard system of units when velocity of light, Planck constant, and Boltzmann constant are just one. This is very convenient. And not only convenient, it also has kind of deep sense to use this unit. So this is velocity of light. Planck constant. And this is Boltzmann constant. So remember that we have energy equals mass and c squared. Momentum is given by the mass and c, or velocity. And the energy, and can be written also as 3kT for bosonic particle. Now, if c is 1 and k is 1, this means that energy, mass, momentum, and temperature can be measured in the same units. So that dimension of energy equals dimension of momentum equals dimension of the mass and equals dimension of temperature. And usually we are using energy units to measure everything. So we are kind of measuring momentum and mass in the units of energy and also temperature. So the main unit in our particle physics is electron volt. So this is the energy which is acquired when a particle with a unit charge passes through difference of the potentials, which is 1 volt. So if it is V, so the difference of the potentials is 1 volt. And then the particle with electric charge, so this is distance, which passes through this potential gets energy, which is 1 electron volt. Now, there's a following connection to the usual units, for instance, ergs. And 1 electron volt equals 1.6 10 to the minus 12 ergs. And 1 electron volt is 1.16 10 to the 4 Kelvin, Kelvin. So, for instance, cosmic microwave background radiation, so electromagnetic radiation which fills all the universe, more or less isotropically, it has temperature 2.7 Kelvin, and this equals 2.3 10 to the minus 4 electron volts. These numbers will be useful for you for solving the problems. Okay. Now let me construct the scale. Probably I will finish by this. Energy scale in particle physics. So let me try to do this in a nice way. So this is the scale. Let me put here. I don't know if the blackboard will be enough. This is milli electron volt. This is electron volt. This is 10 to the 3 electron volts. So let me put here, which is, we call TeV, kilo electron volt. Then mega electron volt. Then giga electron volt. So MeV is 10 to the 6 electron volts. GeV is 10 to the 9. electron volts. Then TeV, tera electron volt. Then it will be PeV. This is peta electron volt, and this is 10 to the 15 electron volt, and this is 10 to the 12 TeV. This is the scale LHC operates, 10 TeVs. Now we can continue this. So then it's EeV. Then it's something which I don't know even the name for this. It's 10 to the 21. So this is 10 to the 21 electron volt. Then it's 10 to the 24. And then it's 10 to the 27. And maybe it's a little bit more. So that's the energy scale we are operating with. Do you see this well? And let me put along this scale some very important values, which are actually very helpful to know. So, remember, maybe we discussed this CMB, which is something like 10 to the minus 4, which is CMB energy somewhere here. This is CMB. I put here along this scale different energy scales and mass scales also. Okay. Now neutrinos, which are probably one of the lightest particles, they are, it seems, in this range. So probably the heaviest neutrino, quite probably somewhere here. So this is mass of neutrino, and is kind of high probability that the heaviest neutrino, and we have 3 neutrinos, the heaviest one has the mass 0.05 electron volt. 0.05 electron volt. So it's somewhere here. Lightest neutrino can be massless still. And the second one is, say, order of magnitude lighter. So lighter. So we know that neutrinos are somewhere here. So neutrino masses are here. Atomic phenomena are here in TeV range. So this is atomic phenomena, atomic physics. Okay, somewhere here. Next important scale is the mass of the electron. And mass of the electron is what? Who remembers this? What is the mass of the electron?
It's 0.7 MeV.
What?
0.7 MeV.
0.5 MeV. So it's somewhere here, right? So this is MeV and this is electron mass. Well, I should say that it's extremely important to remember at least some scales. And then in your heads, you can create kind of a rule how you can reconstruct out of these few scales all other scales. There's certain logic how you can put all the kind of scales and restore them knowing just few important. The electron mass is extremely important scale. So electron mass is here. And you see already kind of interesting, masses of neutrinos are here, and there is a big gap. And we have electron mass here. Now, another important particle is muon. Oh, let me write here that mass of the electron is 0.511 MeV. Half MeV, maybe it's no need to remember, maybe this 11. You can always look in the tables of particles. But for discussions, it's important to remember at least some numbers. Now, next important scale is particle is muon, which is quite similar to electron, but have heavier mass, and the mass is 105 MeV. So this is mass of the muon, second lepton. Now, what is mass of the proton? Who remembers? The mass of the proton is somewhere here. Remember, these are orders of magnitude. It's kind of not a joke. So here is the mass of the proton. Don't forget that the proton is heavier than muon, and of course heavier than electron, right? Now, mass of the pine, I missed it. It's also extremely important particle. It's somewhere here, slightly heavier than muon. And it's also important to remember. So this is muon, and the mass of pine, so this is mass of pine meson. It's somewhere here, very close. This is 105 and this is 140 approximately. So this is mass of the pine. And this is very important particle because of, remember, so the first theory, maybe some of you remember, was Yukawa theory of strong interaction, and precisely pine was introduced as mediator of the strong interactions. So this is very important particle, especially in the strong interaction physics. There is another important scale somewhere in between here. So let me put it here. You may probably have nicer to it. It's CQC, lambda QCD. It's around 300 MeVs. This is important scale for strong interaction physics, and lambda QCD, this scale is precisely where the coupling constant go to infinity. And here is strong interaction or non-perturbative physics and strong interactions. Lambda QCD. Okay, it's here. Now, what else? Sorry. I don't hear you.
Aulia sta registrando. Cioè l'unica che mi sono connesso io.
So I cannot hear. Okay, so let me finish this and then I can probably discuss more. Now important other scales are the following. The mass of the W boson is somewhere here around 82 GeVs, mass of the W boson. And this is scale of weak interaction. So W boson is a particle which is responsible for weak interaction, and its mass is here, slightly heavier, another particle, Z boson. So that's mass of the Z boson. And essentially, these particles determine the scale of weak interactions. You see, strong interactions have this scale, and this is the scale of weak interactions. Electromagnetic scale is somewhere keV. This is typical atomic scale. Now, what else? The heaviest particle, which we know. No, first, let me put here Higgs boson, extremely important particle. Mass of the Higgs, 125 GeVs. It's here. So Higgs is heavier than W boson and Z. So this is the particle which was discovered in the last one in the standard model. Now the heaviest quark is top quark. It's somewhere here. So the mass of the top quark, and mass of the top quark is 175 approximately GeVs. Then LHC scale. LHC has 13 TeV scale. Later I will explain also. So the square root of S invariant mass, I will discuss this later, is 13 TeVs. And it will be probably 14 TeVs soon. So it's 10, and this is the highest scale which we have created at accelerator. So LHC scale is here. And then we don't know what happens after this. So we know that there's a Planck scale, and Planck scale, which is 1 over square root of Newton constant. And this is something like 1.2 10 to the 19 GeVs, which is 10 to the 28, it's somewhere here. So here the Planck scale. We also observed some phenomena of high energies or ultra high energies somewhere here. So for instance, highest energy is cosmic rays, particles which arrive to us from cosmic space is somewhere here or even here, even bigger. So it's cosmic rays. And in particular, the interesting object is very high energy cosmic neutrinos, and they are up to PeV scale. So here we actually see neutrinos arriving to us from cosmic space and accelerated to such a high energies. Now the big question is, what is here? You know, it's kind of very strange arrangement because we have a lot of stuff here. We have something here, mass of neutrino, and probably Planck scale, and who knows what is the real meaning of this Planck scale. This is something which we cooked in this way. But some people are saying, no, this is kind of effective scale, and it can be made out of other scales. So this is what is called high energy desert. But there is also low energy desert because we don't know what is here. This is low energy. And in the recent years, there is a lot of activities to explore if we can find something here. So to say, particles with very small masses, or some phenomena which is very small energies. So probably axions, maybe some of you have heard this, maybe are sitting here. Maybe there's a whole world here. So people are saying maybe we have also dark sector in the universe. And maybe it's populated by particles which are sitting here. So I think I will finish. And please ask questions. Well, I would advise you strongly to really reproduce this scale, this energy scale, and we will discuss different particles. And you can put particles which we are discussing along the scale. This is very useful. I will discuss in the next lecture also this, to kind of have a general picture. We actually do not understand this picture, I should say. We don't know why we have leptons here, lepton here, and there's also the third lepton, which is something like 2 GeVs, which is somewhere here. Why we have so big spread? The mass of the electron is here, and mass of the top quark is here, so we have big split here. And then huge split here. Maybe there is a grand unification here, which is 10 to the 16 GeVs, 10 to the 16 GeVs, which is, what is this? 16 plus 925, so maybe something interesting happens here. Maybe there are so-called right-handed neutrinos, and right-handed neutrinos are somewhere here, but all this are speculations for time being. So that's kind of the present view of what we have. Questions?
I have a question, Professor, but about when we define the characteristics of the quantum object. Mm-hmm. It's just why we define the spin as an external characteristic instead of an internal thing. Mm-hmm. That's my question.
So spin is kind of invariant when we have rotation, right? So in this sense, it fills external space. We affect by spin, by making rotation. But of course, spin is also important for interactions. It's important because you have conservation of total angular momentum and things like that. So in this sense, you can say it also plays the role in interaction, of course.
Okay, okay, thank you.
Mm-hmm. Some more questions?
I have a question about how exact we know the theories. For example, I mean, if we have a theory that gives you a good result in one experiment, but in other experiment is not too good, I mean, not too exact, how we know if the theory is good or bad, if we have those cases?
Well, if it contradicts at least one of the data, then it's already bad, right? So it means that it's not complete, and then one needs to clarify what's going on. For instance, standard model, as it was formulated in the beginning, predicted 0 masses of neutrinos. Then finite neutrino masses have been observed. And now the question is, so what we should do with the standard model? And it turns out that you can add something to the standard model in such a way that you get neutrino masses without destroying everything else. So without destroying nice predictions and nice properties of the standard model. So it depends on what is kind of the level of contradiction. So usually if you have some disagreement, then people try to add something, not say substitute completely the standard model. Now standard model is tested very nicely to very high scale, to very good precision. And if you have some contradiction or some new data which actually do not fit the standard model, then most probably you need to add something to the standard model to satisfy the data. So we have still some anomalies which cannot be described in the standard model. I will mention probably some of these anomalies, like in B physics. And there are some other observations which on the first side cannot be explained in the standard model. So dark matter in the universe cannot be explained in the standard model. And so one needs to add something to the standard model. Some other cosmological observations may also not be explained in the standard model, like baryon asymmetry in the universe. So probably inflation cannot be explained. So still there are some observations which do not match the standard model, but a general idea is that one should introduce something which explains this data but not destroy the standard model. So that's kind of the concept. Okay?
Yeah, I see. Thank you.
Hmm?
I have one question. If the particles has a structure, how are the characteristics of symmetry changed?
Well, you know, for instance, they may not be changed. So that, for instance, electric charge. So if you have even atoms, so an atom, for instance, has a neutral atom. Take neutral atom. It consists of electrons and the nuclei, which are charged particles. However, the sum of the charges is 0, and therefore structure in this sense doesn't change the global characteristics. So it may happen that all these characteristics which we are discussing here, they will not change, but there are some substructures. arranged in such a way that they reproduce these properties or these characteristics we are discussing.
Okay, thanks.
So, you know probably my email address. If some of you wants really to discuss some more in great details, you can just send me mail and we can arrange the meeting. For time being, it is not allowed to meet in a big group. I hope again that the things will change. I don't see any kind of really serious reason not to have you in this hall, because we still can keep big distance and open window, and it's not more danger than to go to canteen, right? So that's the argument I just don't see. I hope we will meet soon in this hall. Well, actually, I came from Germany to give these lectures, so I'm in this hall, and it was a decision that we are giving the lectures in person, and therefore, specifically for this, I came from Germany 8 days ago or so. Okay, so then I will see you tomorrow, right?
I have one question, no actually question. Like what book, like what book exactly we should refer to understand more about the subject matter?
Well, first of all, this is kind of introductory lecture, right? So I just marked some important things, and we will discuss many details of what I was saying today. So we will discuss discovery of pi, and we will discuss discovery of top quark, etc. And then we will repeat many things, but in more details than it's now. And I will then give you the list of sources, books, and reviews, which you can use also to have a deeper look at all these things.
Thank you.
Okay, so then see you tomorrow.
See you tomorrow.